My dear friends, welcome back to BSpice. In this session, we will be discussing about the PRV, pressure reducing valve or pressure regulating valve, wherein we specifically target two items for discussion: body outlet velocity and valve opening. Of course, prior to this, like 6 months back, we have uploaded so many videos on the PRV sizing. If you are really interested, you can watch and get benefited. But this particular video is exclusively for the BSpice member. As you know, I always respect BSpice members, and without them, BSpice, would not have traveled this much actually. The backbone behind BSpice is only the members. So I'm actually, want to support wholeheartedly. That is why I thought of, uploading this for everybody. Okay. So let's go with the question. What was the first question? Yes, for instrument as service with pressure reducing type, do we need to check the outlet velocity limitation? Outlet velocity limitation like we do in the control valve. Yes, in control valve we do check. So here the answer is yes, but with different priorities. This is very important. Outlet velocity is a critical factor in control valve sizing due to noise, erosion, and flow stability, right? So for pressure reducing valve PRV in instrument as system, velocity is generally less critical, but still worth checking in specific scenarios. Okay. Since we talked about the noise, I also want to, share this. I hope this is not an issue, friend. I'm sharing this for the, for explaining this query. Okay. Maybe before that, I'll go into the pointer mode so that it will be easy. Yes. So as you can see here, friends, this guy, predicted noise, it's less than 70. So noise is not a factor at all. So now you know the answer right already, but nevertheless, I will explain further. Okay, I'll go into the next slide. Okay, here I want to compare the control valve with PRV. Friends, control valve outlet velocity is tightly controlled to avoid, aerodynamic noise, vibration, erosion, especially in gas and steam application. ISA IEC standards provides a velocity limit based on the valve type and service. In fact, we also covered this. You can also watch if you are really interested. Okay. So when you talk about the pressure reducing valve PRV, they are typically self-operated and used for steady pressure regulation, right? So they do experience velocity changes. So the design is often more, forgiving. I mean, we don't have to go much worry about that unless the outlet piping is small or long, okay? Risk of high velocity and pressure drop, okay? So when we talk about this outlet piping is small actually. As you can see here, friends, maybe I'll just, blow up a bit. One moment. Yeah. You see here, friends, the outlet, what is that? We are talking about outlet piping, right? Yes. So one moment. Just blow up a bit. Yeah. So out the pipe you see here, friends, it is 3 inch actually. So that is not too small. Okay. That is the point. It's 3 inch. As you can see here, it is 3 inch. Again, I go into the presenting mode. Yeah, sorry. Yes. So it's a 3 inch. It's not so small. Okay. So the point is we do experience velocity changes. The design is more often forgiving unless the outlet piping is small. So here that is not the case. You got it? Okay. Then pressure drop. That is also we should see actually. Risk of high velocity and pressure drop. So where is the pressure drop here? Not much actually, 0.7. Minimum, minimum is 2.7, right? It is also not much. Okay. Now, second, the downstream equipment is sensitive to turbulence or noise. If the downstream equipment is sensitive, I don't know what is the downstream equipment in this from the data sheet. Friend, you can check whether the downstream equipment is sensitive to turbulence or noise. So you can check and also comment for the benefit of others. You can comment in this video. So the downstream equipment is sensitive to turbulence or noise. Anyway, the first point is the noise is not that much in this. Okay. Then the flow rate is high relative to the valve size. So here it is 3 inch and flow rate is high or no? Not much actually. If the flow rate is very high related to the valve size, then we do consider that. Okay. So these are the aspects we should kept in mind when we decide this body outlet velocity. Okay. Right. Now I go into the when to check the outlet velocity in PRV. Okay, we should evaluate outlet velocity if the noise or vibration is a concern in the downstream piping. Here, at the first case, the noise is not an issue. Okay, then airflow rate is high or the pressure drop is large. Pressure drop is not very large. Okay, airflow rate is also not that much high. Okay, so if you are using a plastic or soft metal piping that could erode. Here, I think it is not a plastic or soft metal. Maybe let me see where is that. I think it is not here actually. What is the line? Material is not there. Fluid is there. I think it's not there. Friend, you can also check from your side. Probably, yeah, from the piping class also we can verify that. You can check from your end. So if you are using a plastic or soft seal metal piping, that could erode. Soft, if it is soft. That case we should consider. Okay. Then the PRV outlet feeds directly to sensitive instruments. So I think here it should not be a problem because this is, just an air application, should not be an issue. So these are the scenario we should check the outlet velocity. Really, we should check the outlet velocity in this scenario. So that is my point. Okay. Now, just practical guideline basically. For our system, we should keep the outlet velocity below 150 feet per second. Or if we say meter per second here, they are given meter per second, right? So 45 meter per second in general piping and below 90 meter per second in short runs or where noise is acceptable. So both the scenario we should, we should, I mean, what do you call, we should ensure this 45 meter per second or 90 meter per second. But in your case, it is well within that. So I don't think any issue at all. Then if you want to calculate, this, you have to use this V is equal to Q by A, where V is the velocity, Q is a volumetric flow rate, A is a pipe cross-sectional area. This is just an add-on. Okay. Now I go into the conclusion. See, we don't always need to check outlet velocity for instrument air PRV, but it's good practice in high flow, high pressure drop or noise sensitive application. So in your case, I think if you ask me, it's not required. Okay, that's it. So the first question is answered. Now, okay, it is not as strict as control or sizing, but ignoring it entirely can lead to downstream issues. So that is why we need to also, consider the flow rate, high drop, noise, pressure drop and noise sensitive. All these we need to see. That is why I caution here. So that you need to check whether it has any impact in the downstream. Right, friends? Right, friend? So that is the conclusion. Then we see the second question, valve opening. What should be the valve opening? Is there any percentage opening that is between 20 to 80% for minimum to maximum flow rate like we do in a control valve? Normally in control valve, we'll consider this, right? The answer is yes, but again, it's not typically specified the same way for PRV as it is for the control valve. Control valve are designed for modulating service and are sized to operate efficiently between 20 and 80% open, right? PRVs, on the other hand, are usually self-regulating and not modulated by a controller, isn't it? So their operating range isn't managed the same way, right? Okay, now to elaborate further, I want to give you the comparison between the PRV and control valve. See, friends, purpose control valve, yes, it's modulate flow based on the control signal, and PRV maintain the downstream pressure. Opening range ideally 20 to 80%, but here not typically specified. Now you got the answer, right? Yes. For actuation, yes, pneumatic, electric with positioners, and this is more of a self-operated with spring diaphragm mechanism. And sizing focus, yes, flow control and rangeability. Here pressure drop and flow capacity matters actually. This is just an add-on for you. Now I go why this 20 to 80% is important for control valve. Yes, because below 20%, it results in poor control resolution, risk of stiction. It gets stick, right? Yes. So above 20%, reduced control authority. We don't have the control, so potential for instability. That is the reason. This range, 20 to 80% ensure good linearity and responsiveness. Right? Okay. Now again for this PRV are not designed for precise modulation across a wide range. Instead, they open or close to maintain a set downstream pressure. So the valve may operate anywhere from nearly close to fully open depending on the demand, but we don't typically size them based on a 20 to 80% rule. However, oversizing and PRV can lead to poor control and hunting, so some margin is still important. Okay, so having said that, friends, as you can see here, minimum is 5, normal 20, and still it is within that 80, 86 actually. So this is not a major challenge at all. Okay, right. Now, best practice, ensure flow rate is within the valve rated capacity. Ensure the pressure drop is sufficient to allow stable regulation. Avoid oversizing to prevent instability. These are the best practice actually. Right. So conclusion, if you are designing a system where precise modulation is needed, of course, control valve is more appropriate. But in this case, if you are maintaining just a set pressure for instrument tab, a well-sized PR will do the job, even if it doesn't follow the 20-80% rule. That's the conclusion, friends. Thank you. Hope I have queried your questions. You can respond in the same, video, if any further thing. Okay, thank you. And keep posting in many questions. Not only you, I'm encouraging all the members to post question so that let us learn together. Take care. Bye-bye.